Welcome back to the deep dive. We've got some really interesting sources today sent in by you, our listener. They cover a new development in AI, quite cutting edge, and definitely on the more academic side. It's called log linear attention.
It's right. It's all about making AI models, especially language models, more efficient and more capable when dealing with really long sequences of information.
Trying to get past some of the fundamental bottlenecks we see with current methods.
Exactly.
So our mission today is to unpack these sources together. We want to pull out the key insights, really focus on what's innovative here, figure out what log linear attention actually is, and why it's generating some buzz in sequence modeling.
Sounds good. It's definitely addressing a core challenge.
Okay, so to understand why log linear attention is a thing, we need to start with the problem it's designed to solve. The foundation for so many powerful AI models today, especially in language, is the attention mechanism, right? Particularly in transformers.
Absolutely. Attention has been revolutionary. It lets the model weigh the importance of different input parts when processing any single part. It's dynamic.
But the standard way it's done, softmax attention, runs into a major issue.
Yeah, it hits a scaling wall. The computational cost, the processing power needed, it grows quadratically with the length of the sequence.
OT being the sequence length, and memory used grows linearly, OT.
Right, and the sources call this quadratic compute and linear memory a fundamental limitation.
Which means for really long sequences, think processing entire books or long conversations, it just becomes too expensive or sometimes literally impossible to train or even run these models.
Exactly. So that led to a lot of work on more efficient alternatives. You have things like linear attention and also state space models, SSMs like Mamba.
And the goal there was speed and efficiency, right? Trying to get the computation down to linear time, OT, and memory down to constant. Oh, right.
Precisely. Get rid of that nasty quadratic scaling. Linear is much, much better for long sequences.
But there's always a but, isn't there?
Often in research, yes. The sources point out that while these standard linear models are efficient, they introduce their own kind of limitation. They typically work by summarizing everything they've seen into a single, fixed size, hidden state. Just one memory slot, essentially.
A simple, fixed-size state. Okay, why is that a problem?
Well, when you're dealing with really long sequences, that fixed state becomes a bottleneck. It struggles to hold on to all the necessary information. The sources mention performance degradation on longer contexts, and it limits capabilities like associative recall, remembering a specific fact mentioned way, way back in the sequence.
Because that single state just gets overloaded or overwrites older, potentially important details?
Exactly. It has limited capacity to retain fine-grained information over long distances.
Okay, so that sets the stage for log linear attention. The sources describe it as a kind of middle ground.
Yeah, that's a good way to put it. It's trying to find a sweet spot, keeping much of the efficiency of linear attention, but regaining some of the expressive power needed for complex, long-range tasks that the fixed state struggles with.
And the core innovation, the really new idea here.
It's how it manages memory. Instead of that single fixed-size state, log linear attention, as the sources state, replaces the fixed-size hidden state with a logarithmically growing set of hidden states.
Logarithmically growing. Okay, unpack that a bit. Not fixed, but not growing linearly either.
Right. As the sequence gets longer, the number of hidden states, or memory slots, increases, but very slowly logarithmically. So if the sequence doubles in length, you only add a small, constant number of new states, much slower than linear growth.
And the goal of having this growing set of states.
The aim is to capture information at multiple temporal scales, as the sources put it. You can have some states representing recent information in high detail and others summarizing much older history more broadly. It provides a richer, multi-resolution view of the past compared to a single fixed state.
Interesting. So how does it actually create and manage this logarithmically growing set of states? The sources get into the mechanics, mentioning something called Fenwick tree partitioning.
Yes, that's a key mechanism. It's not that the model is a Fenwick tree, but that the structure of a Fenwick tree inspires how the input sequence is divided up.
How does that work?
It's a scheme to hierarchically partition the input into power of two-sized segments. Imagine looking back at the sequence you've processed so far. This method divides that past history into segments of lengths 1, 2, 4, 8, and so on, covering the whole history.
So you end up with these buckets of different sizes representing different time spans.
Exactly. And crucially, the number of these buckets only grows logarithmically with the total length of the sequence processed so far. That's where the logarithmic growth comes from.
Okay, and why this specific power of two partitioning? Is there an advantage?
The sources argue yes. It naturally emphasizes recent tokens through finer segmentation. The most recent parts of the sequence fall into the smallest buckets, size 1, 2, etc., giving them finer grained representation. Older history gets grouped into larger, coarser buckets.
Ah, so it builds in a kind of bias towards recent information being more detailed, which makes sense for many sequence tasks like language modeling.
Precisely, it's an inductive bias, but it still retains summaries of the older information in those larger buckets, accessible via the logarithmic structure.
And within this structure, they also use adaptive weights. The sources mention data-dependent scalar weights.
Yes, this is another crucial piece. For each of these buckets, or temporal scales indexed by O, there's a weight lowest that the model learns based on the current input token. This weight determines how much influence the information stored in that specific bucket has on the current prediction. So the model can dynamically decide which timescales are most important right now.
So it's not just a fixed hierarchy. The model learns to adaptively use the different levels of memory.
Correct. It leverages that multi-scale structure dynamically.
This hierarchical partitioning and adaptive weighting, it leads to specific efficiency benefits related to the structure of the attention matrix.
Exactly. The way this partitioning works induces a very specific mathematical structure in the attention masking matrix, the matrix that determines which tokens can attend to which others. The sources call it a quasi-hierarchical matrix, MH. It's related to a class of matrices called hierarchical matrices, specifically a type known as HODLR. The quasi part is a technical detail about its specific properties.
And the key takeaway from this matrix structure.
The sources state the structure is crucial in enabling O log T complexity during inference.
Okay, there's the logarithmic efficiency. Because the memory is organized hierarchically, according to this matrix structure, accessing and updating it for each new token only takes logarithmic time relative to the sequence length t.
That's the core idea for inference or decoding. The sources clearly state the resulting efficiencies. OT log T compute costs for the entire training process.
Which is better than OT2 for standard attention.
Definitely. And then for inference, for generating one token at a time, it's O log T time and memory costs per step.
Let's compare again. Softmax is OOT train, OFT inference memory, basic linear is OT train, O1 inference memory, log linear is OD, log T inference memory.
Exactly. It sits in an interesting spot, trading a slight increase in training costs and inference memory over basic linear models for potentially much better handling of long contexts, thanks to that logarithmic state.
And how do they actually train it efficiently, achieving that OT log T?
They adapt an approach used for linear attention called the chunk-wise parallel algorithm. You split the long sequence into smaller chunks. Calculations within a chunk can be done very efficiently using standard, fast matrix multiplications, matmul-rich operations, great for GPUs. The interactions between chunks are handled using the properties of that special MH matrix structure. That interchunk processing is what introduces the log T factor, leading to the overall OT log T training complexity.
Clever. So it balances parallel processing within chunks with efficient handling of the longer range dependencies between them using that hierarchical structure.
Right. It's a combination of algorithmic and structural insights.
The sources also emphasize that this isn't just one model, but a general framework. What does that mean?
It means log linear attention isn't necessarily a completely new architecture from scratch. It's a technique you can apply to existing linear attention models, or SSMs. Essentially, you take the original model's attention mechanism, particularly its masking matrix, let's call it MS, which is often structured for efficiency itself, and you combine it with this new hierarchical mask, MH, derived from the Fenwick partitioning. The final mask, M, becomes a combination, like M equals MS element-wise multiplied by MH.
So you can enhance existing models like Mamba-2 or Gated DeltaNet with this logarithmic memory capability.
Exactly. The sources give those as specific examples, log linear Mamba-2 and log linear Gated DeltaNet. They're created by integrating the MH mask into the original Mamba-2 and Gated DeltaNet structures. They still retain their core differences, like Mamba-2 using scaled identity matrices versus Gated DeltaNet's delta rule updates, but they both gain this hierarchical logarithmic memory structure via the MH mask.
Okay, that makes sense. It's a modular improvement. So the theory and mechanics sound promising. How did it actually perform in practice? What did the experiment show?
This is where it gets interesting, seeing if the theory translates. The sources show quite positive results, especially on tasks that really push long context understanding.
They mention a metric called per position loss. What does that show us?
Per position loss tracks how well the model predicts the next token at every single position in a sequence. Ideally, for a model using long context, while the prediction error, the loss, should decrease as it sees more context even way out at position 10,000 or more.
And did the log linear models show that?
Yes. The sources show plots where log-linear Mamba-2 and Gated DeltaNet consistently reduce the smooth loss across various positions compared to their non-log-linear counterparts. This strongly suggests they are using that long-range context more effectively.
Okay, that's a good sign. What about more direct tests of retrieval, like that needle in a haystack benchmark?
IIH is a fun one. You hide a specific piece of information, the needle, somewhere in a very long document, the haystack, and see if the model can find it when asked.
And the results?
Pretty convincing. Log-linear Mamba-2 beat the standard Mamba-2 on 8 out of 9 single-needle tasks, and log-linear Gated DeltaNet improved performance on all the multi-needle tasks they tested, shows a clear benefit for pinpointing information in long texts.
What about synthetic tests, like associative recall?
They used a benchmark called MQAR. Here, log-linear DeltaNet kept high accuracy even as the sequence got very long, while the standard DeltaNet's accuracy degrades significantly, again pointing to the advantage of the hierarchical memory for recalling information over long distances.
So strong results on targeted and synthetic tests. How about broader real-world benchmarks like LongBench?
LongBench covers a diverse set of long context tasks. The log-linear versions of Mamba-2 and Gated DeltaNet outperform their baseline linear versions in 8 out of the 14 tasks evaluated, so a solid improvement across a range of realistic scenarios.
And in-context retrieval tasks, like question answering on long documents.
Gains there too. Log-linear Mamba-2 improved on about half the tasks, like squad trivia QA, while log-linear Gated DeltaNet showed more consistent gains. So definite practical advantages are showing up.
That's impressive. And you mentioned the efficiency wasn't just theoretical, they built a fast implementation.
Right. They developed a custom Triton kernel that's a specialized piece of code for GPUs for log-linear Mamba-2, and they found it actually outperforms Flash Attention 2, which is a highly optimized standard attention implementation once sequences get longer than 8,000 tokens.
Wow, so it's actually faster in practice for long sequences during training, despite the slightly higher theoretical complexity compared to basic linear attention.
Exactly. It shows the practical viability of the approach on modern hardware.
How do these models do on standard, shorter context tasks where maybe the log linear structure isn't strictly necessary?
Performance was generally comparable to the baselines. Interestingly, log-linear Gated DeltaNet actually showed stronger gains in some cases, even beating a transformer of similar layer count across all metrics they checked, and matching a parameter-matched transformer on half.
So the structure might offer some benefits, even when ultra-long context isn't the primary focus.
It seems possible, yeah. The hierarchical representation might just be a generally useful inductive bias in some cases.
Overall, it sounds like a significant step forward, especially for this long context challenge. But like any research, there are caveats and limitations, right? The sources were upfront about those.
Absolutely. They're clear it's not a magic bullet that solves everything. A key point is that a significant performance gap compared to transformers also persists across all benchmarks in some areas.
So while it improves on linear models, it doesn't necessarily match the absolute quality of top transformer models on every single TAD yet.
Correct. There's still room for improvement to close that gap universally.
And what about the complexity of actually using it?
That's another point. They mention higher engineering complexity. The algorithms, especially for the efficient training, require bespoke implementations. They're not standard, off-the-shelf layers you can just drop in easily everywhere.
The backward pass for calculating gradients during training is also more complex.
Yes, described as more intricate, particularly needing manual gradient calculations for those adaptive lambda weights. So it takes more specialized effort to implement and optimize compared to simpler architectures.
And that built-in bias from the Fenwick tree, petitioning favoring recent information.
While often helpful, they acknowledge it leads to an aggressive compression of distant tokens. This might not be ideal for every single application. If a task requires extremely fine-grained recall of very old information just as much as recent info, this specific bias might be suboptimal.
Makes sense. Different tasks might need different memory structures.
And they also mention that fully exploring the best way to parameterize those adaptive lambda weights is an open area for future research. They couldn't exhaust all possibilities.
Okay, stepping back a bit, how does this fit into the broader research landscape?
It clearly builds on a lot of recent progress in efficient sequence modeling. Ideas from structured matrices like hierarchical matrices are relevant, And it directly extends specific prior work like linear attention mechanisms and the Mamba SSM lineage, particularly Mamba-2 and Gated DeltaNet.
And the use of the Fenwick tree structure for partitioning is that the main differentiator from other attempts at similar goals.
Yes, the sources highlight that specific partitioning scheme inspired by the Fenwick tree's power of two structure as key to achieving their specific O log T inference and O log T training complexity results, setting it apart from some earlier approaches like reformer or others that aimed for logarithmic complexity via different means.
And we should probably mention the researchers involved. It's often a team effort.
Definitely. The paper credits Han Guo and Songlin Yang from MIT as co-first authors. Other authors include Yoon Kim, also from MIT, Eric P. Sheng from CMU and elsewhere, and significantly Tri Dao from Princeton and Together AI, who's very well known for flash attention and Mamba-2.
And Albert Gu, also closely associated with Mamba and SSMs, provides important context for the Mamba-2 baseline they build upon. It's a strong group working at the forefront of these ideas.
A very active area of research.
So to wrap up our deep dive here, log linear attention seems like a genuinely novel and, yes, academically rigorous way forward for efficient sequence models.
Right. It introduces this idea of a hierarchical, logarithmically growing memory using that Fenwick tree partitioning idea. It strikes a new balance, aiming for linear-like efficiency, but with better long context abilities than standard linear models.
And it's a flexible framework shown to enhance existing models like Mamba-2 and Gated DeltaNet.
With clear empirical wins on important long context benchmarks, plus demonstrated practical hardware speedups.
But, as the sources note, there's still that performance gap with the best transformers in some cases, and the engineering is more involved. Plus, the specific bias of the Fenwick structure might not fit every task perfectly.
Which leads to a really interesting closing thought, doesn't it? Given those points, the remaining gap, the specific recency bias, what's next?
Yeah, what other kinds of hierarchical structures or partitioning schemes could researchers come up with? Could there be ways to get different trade-offs, maybe better suited for tasks where, say, very distant information needs just as much detail as recent info?
Or perhaps hybrid approaches. It feels like the design space for efficient, long-context sequence models is still very much being explored. What kind of structure provides the best inductive bias across the widest range of tasks? That's still an open question.
An excellent point to leave our listeners with. The search for the perfect long sequence architecture continues.
Indeed.
Well, thank you again to you, the listener, for providing these sources. This was a fascinating look into log linear attention.
It really was. Great material.
Until the next deep dive.